Hello and welcome to another session with Elimika. In this session, we will be discussing significant figures as the second sub-unit of our first unit on numbers. Okay. In this session, this is an important subtopic. It is not only applicable to area of mathematics, but also to the sciences. Okay, so especially physics students, we use a lot of calculations where answers are supposed to be given to specific number of significant figures or given number of decimal places. As a matter of fact, what we'll do here is to use two very simple rules for significant figures. This will be different from what you'll find in textbooks where a host of rules are given for different types of numbers. I think there can be as many as 5. We will simplify this process and use 2 basic rules to be able to determine the number of significant figures in a number. Okay, let's begin this session. Consider a situation where there is a music concert and 3 different individuals are required to report the attendance of the concert. All right, we have your friend who reports attendance of the musical as 10,000, that there were 10,000 people in attendance. Another person here would be the local sports journalist who reports that there were 12,600 people. It could be a sports journalist or a music art journalist, reports 12,600 people, and the chief firefighter of the stadium reporting 12,613 people. I want us to consider a number of questions regarding this report by 3 different individuals. Okay, so your friend says that tells you that there were 10,000 people who attended the musical. A journalist says that there were 12,600, and a firefighter insists that there were 12,613 people. The question I want to pose to you, a number of questions that I want you to think about is which figure is more realistic? Okay, think of that term realistic. All right. Another one, which figure is the most reliable? What does it mean, reliable? Okay, dependable. Another question is, which figure is the most practical? So the practicality of the figures being given. All right. So practicality is a relative term, really, because it depends on who these are. Right. Lastly, actually not last, second last, who needs practicality? So among these, who needs this figure to be practical and who needs it to be reliable and why? Right? So this is to understand what we mean by significant figures. What is the significance of significant figures? And lastly, why is it acceptable for a journalist, for example, or even your friend to say 12,600 as the attendance, but it is dangerous or even criminal for a firefighter to report a value of 12,600 if there were 12,613. These are questions I want you to think about, so you can pause the video and think about an answer you would give to each of these. Okay? And let's go on. Well, of course, the firefighter has reported 12,613, in other words, the exact number of people who are inside the stadium, because in case there is a fire, they want to be able to account for every individual that went in to watch the music concert, right? So we can say that the firefighter has to report to 5 significant figures. All the digits are significant. The journalist does not have to report all the digits because the journalist is trying to give a general feel of what the attendance might have been like. Very few people really needs to know the exact figure, all right? Practicality or the use of these figures. So we don't usually really need to know what the figures are if we are not a firefighter or if we are not the people at the gate collecting the fee we are not really interested in the exact figure. So knowing an approximate value of the number of individuals that were at the stadium is just enough. So saying 12,600 is more than enough information to be given by a journalist. Okay, so we can see that the figure that the journalist gives ignores the 1 and 3 because in terms of reporting to the general public, the 1 and 3 are not really that important. We say the 1 and 3 are not exactly significant. Okay, in that case, we can say that there are only 3 significant digits in the number that is reported by the journalist, because for a journalist or for the general public, the 1 and the 3 are not really significant, are not important. Okay, so the figure given by the journalist has been quoted to 3 significant figures. 3 digits they are important, the last 2 are not important or are not significant. And what about your friend? Your friend reports that there were 10,000 individuals. It's possible that your friend did not even know what the number was, so it would even be sufficient to say the stadium was filled to capacity. All right? So that such information would be enough coming from your friend. They don't even have to give a figure. So giving a figure of 10,000 indicates that this individual ignores the 2, the 6, the 1, and the 3. We can say that those 4 numbers are not significant when your friend is reporting to you about the capacity of the crowd at the concert. All right? And so we can say here that your friend is giving just 1 number that is considered to be significant. Okay? And so the answer given by your friend there, is correct to 1 significant figure. We can say that the 2 zeros here or the 4 zeros there are put there as placeholders. A placeholder is to ensure that we remember this figure is in 10,000s, okay? So if we don't put those 2 zeros there, then we have 126, which will not be giving us the value of the attendance. So we have to put those 2 zeros to as placeholders to ensure that the figure we are talking about is still of the same order of magnitude, the same order of size as the figure given by the firefighter. Okay? And so the 2, the 6, the 1, and the 3 are not that important to you when your friend is reporting the attendance to you. So like I said, your friend might as well just say that the stadium was filled to capacity. There were so many people, and that would be enough without even giving a figure. All right? So the way we report a number depends on how useful that number is. So I want to go back slightly so that we can look at this. So which figure is realistic? So obviously, it's highly unlikely that the attendance would be exactly 12,600. Okay, it's highly unlikely. It is possible, but very unlikely. So it's not really realistic. Similarly, exactly 10,000 attendance is not realistic. So the most realistic figure is right to the last digit. Okay, so that is being realistic. Which figure is reliable? Once again, the figure given by the firefighter is more reliable because he gives the exact number of people that have gone in. We would not rely on these figures because they are just approximation. Okay? Which figure is practical? So practicality depends on who is using the information. Well, for your friend giving you information about the attendance, this is practical as far as you are concerned because you do not need really to know the number of people, the specific number of people that were inside the stadium. So for you and your friend, this figure is already as practical as it can be. Okay? Similarly, 12,600 would be sufficient for the general public because the general public does not need to know all that detail in the last 2 digits. And in the same way, for the firefighter, the 12,613 is the practical figure. Those who are collecting a fee at the gate also will require this number to be the most practical. Okay, so who needs practicality and who needs reliability? So practicality means all these people need practical figures to be given to them. They do not need, the friend and the journalist do not need this figure. So for them, these figures are more practical. All right. So practicability depends on who the information is being sent to. On the other side, reliability. Okay. Reliability is now a question of how important that data is, and that is to say, this becomes more reliable compared to the others. Okay. So if I wanted to collect fees, then I would not be going for these figures. I would go for a more reliable data. If I want to bring in firefighters, or I want to check that everybody is available, there is a fire at the stadium, then I'm going to bring data by the firefighter because it is more reliable when it comes to saving lives. Okay? So why is it acceptable for a journalist to report 12,600 but dangerous or even criminal for a firefighter to report 12,600? Well, the firefighter must report the exact number of people inside the stadium so as to ensure that in case the fire breaks out, everyone can be saved. We do not leave anybody behind. On the other hand, so if he reported this and it turns out that 13 people were left inside, then of course it would be a criminal offense. Okay? It would be dangerous and it would be a criminal offense. All right, let's move on. So we've looked at this. So we can say that your friend reported the figure or the attendance to one significant figure because only one digit there is important. We've ignored all the other four. All right. The journalist has reported their figure to 3 significant figures, as you can see, and the firefighter reports it to 5 significant figures, 5 important digits. Right, let's move on. Significance in decimal places. So we've looked at significant figures involving whole numbers, number of people in a stadium. Those are whole numbers, but we can also have decimal numbers. And how do we see significance in decimal numbers? Here is an example of using a ruler to measure the length of a drawing pin. So here is a drawing pin. I'm going to place it against that end of the ruler. So the ruler measures in centimeters. Okay. On the other side, I'm going to put a marker and take a moment and record or try to take the reading for the length of that drawing pin. What do you think that length is? All right. Well, if you look at that carefully, you should be able to see that that is a length of about 4.3 centimeters. The reading is in centimeters. So it tells us that the length of that drawing pin is 4.3 centimeters. However, if we look more closely at the marker there, you can see that it is slightly to the right of the third marker, the 0.3. So the 0.3 is somewhere here, and our marker is actually slightly ahead. So it's not exactly 4.3, it is 4.3 something. If we used an instrument that is more reliable, such as a vernier caliper, it might give us something like, so a vernier caliper is a better instrument than a ruler. It gives us values to better number of decimal places. So it might give us something like, 4.31 or 4.32. In that case, we now have 3 digits that are important. So the last digit there becomes important if we are using the vernier caliper to take measurement. Okay. Also, even if the vernier caliper gave us a value of 4.3 exactly, when we report this reading, we would still put 4.3, but we would place a 0 at the end instead of the 1. So we would have a value of 4.30 like that if we were using the vernier caliper. So placing a 0 here is important because, 1, it tells us that the reading might be ahead of 4.3. That's one point. The second thing is it tells us that the instrument that was used to take this measurement is an instrument that can record to a higher number of decimal places, to 2 decimal places as opposed to 1 decimal place that the ruler can measure to. Okay, so that 0 there becomes important because it gives us some information. It tells us the reliability of the measuring instrument. Okay, so for that reason, the 3 is useful, it is important, it is significant. All right. Clearly, this 0 is important or it is significant because of the things that it tells us. Okay? And that reading, both readings here, were therefore considered to be to 3 significant figures. That is just to explain why knowing the number of significant figures can be important, especially to scientists that record, those who record data that come in decimals. All right. Calculation. If you had a choice to choose between decimal numbers and whole numbers, you'd probably go for whole numbers. So whole numbers are always right is the slogan that we will use to determine the number of significant figures, right? Applying the slogan. So we say that if you are given a whole number, if we want to know the number of significant figures in a number, if we want to know the significant figures, how many there are in a number, then we want to use this rule, that whole is to the right. So start from the right of the number and count all digits starting with the first non-zero digit. That's the first rule. There are only going to be 2 instead of 5 that you'll find in the book. So given a number, look at the number, start from the right of that number, the right is this way, and count all the digits starting with the first non-zero digit. Okay, let's see how we do that. Example. So here is a number 510. 510 is a whole number. It does not have a decimal on it. Okay, so because it is a whole number, we go to the right of the number and we are going to count the digits, but we must start with the first non-zero digit. Okay, we will start with the first non-zero digit coming from the right and going that way. The first non-zero digit we find is 1 followed by 5. Okay, we are told to count all, but we must start with the first non-zero digit. So there is a 1 there and there is a 5, so there are 2 numbers, okay, counting from the right. And so this number 510 is given to 2 significant figures. That's it. Let's see another one. All right, 10,510. How many significant figures does this number have? So once again, this is a whole number. It does not have a decimal point on it. So we start counting from the right and count all the digits, but we must start with the first non-zero digit. So 1, 2, 3, the 0 is now counted because after the first non-zero digit, we count everything. So 1, 2, 3, 4. So this figure is to 4 significant figures. All right, the number 10,510 has been given to 4 significant figures. Let's see another one. 72,413 is a whole number. So we start from the right. If it is a whole number, you start from the right and count all the digits, but starting with the first non-zero digit. So here we start immediately from 3, and you can see that we have 5 significant figures. So 72,413 has been given to 5 significant figures. Let's go to the next one. I believe one more. Yes, there it is. Now we have 700. We can see that for 700, starting with so now we have 700. We can see that for the 700, if we start from the right, we will leave the 2 zeros because we must start with the first non-zero digit, and we only end up with the 7 there, and that tells us that 700 is given to one significant figures. We will discuss circumstances under which 700 could be 3 significant figures or 2 significant figures, but from the onset, we will take this to mean one significant figure. If it is not, it will be given in another form. All right? All right. Hoping you've understood that. Let's apply the slogan otherwise. So what happens if it is not a whole number? If it's not a whole number, then it is a decimal number. And if it is a decimal number, then we start from the left. So remember, if it is whole, we start from the right. So you just need to remember, when it is whole, we start from the right. The other one will come automatically. So if it is a decimal number, then we always start from the left of the number and count all digits, same as before, and starting with the first non-zero digit. So we are either counting from the right or we are counting from the left. If we are counting from, whether we are counting from the right or from the left, we start with the first non-zero digit and count everything. That's all about this rule. All you need to remember is that when it is whole, then it is right. We start from the right. Okay? So now it is a decimal number. We always start from the left. Here are examples. Here is a decimal number. 51.0 is a decimal number. Okay? How many significant figures are there? Well, now we start from the left and we count starting with the first non-zero digit and then count all the digits. Okay? So the first non-zero digit is of course 5. All right? Then there is a 1 and there is a 0. We count all of them, provided what we start with is a non-zero digit. We count everything after. So clearly, this is telling me that 51.0 is to 3 significant figures. Okay, let's see another one so that you are certain you are understanding what's going on. All right, how about 10.510? So given 10.510, it is a decimal number. So we start from the left. We count all digits provided we start with the first that we meet. With the first non-zero digit that we meet, we start with that. And then count everything after that. So the first non-zero digit is 1. So now we count everything after that and we can see there are 5 digits there. So this figure is to 5 significant figures. All right. Another one, 72,413.0. How many significant figures are there? Please pause the video and try to figure out how many significant figures this number has. Well, if you've done the correct thing, then you should have found that there are 6 significant figures to this number. All right? Let's see. There is one more. 0.00700. How many significant figures are on this number? Please pause the video and see if you can get it before I give the answer out. All right, so we start, it is a decimal number, so we start from the left and we count starting with the first non-zero digit. So we move on until we find a non-zero digit, which is 7, and then we count everything. So therefore, there are 1, 2, 3 digits there. So 0.00700 is a number given to 3 significant figures. Okay, I'm hoping that is clear. Let's see if we understand this by looking at some readings from measuring instruments. So these are instruments we use for measuring different quantities. Here is the first one. So the question is, state the number of significant figures or digits shown on the device. This is a measuring device. The first one is a device used for measuring a quantity called voltage. Physics students will be going through this. So this instrument is called a voltmeter. The reading there is 480. So it's reading 480 volts. Ignore everything like volt and so on and just look at the number purely. All right, don't think physics, it's just numbers. How many significant figures are there on this number? Well, 480 is a whole number and whole is positive, is right. Okay, so 480 is a whole number and whole is right. So because it's a whole number, we must start counting from the right Okay, start with the first non-zero digit, and the first non-zero digit is 8, and then we count everything after that. So what we have here, 480 has been given to two significant figures. I'm not writing that down so that you can actually do it yourself, okay? So I will give that as an example, and then now look at these others, and I want you to give your values. We can discuss those later. If you have any question, you can post it in the comment section. So the next one is what we refer to as an infrared thermometer, the one you point like a gun at a source and you get the reading. So this one is reading 36.8. How many, write the number of significant figures that 36.8 has, okay? How many significant figures are those? All right, here is another one. This is an analog thermometer. All right, this is usually placed in on a wall to read the temperature and humidity and stuff like that. So this one is reading approximately 68 or 67. You can pick any figure. How many significant figures is 67 or 68? Okay, next is a pH meter. A pH meter, you put the sensor in a container that is carrying your chemical if you want to determine what the pH value is. And this one is reading 7.474, which is to say this is almost neutral, right? Because pH of 7 is neutral. It's leaning a bit towards alkalinity. The question is, how many significant figures are there on that reading? Okay, the next one. This one is a digital micrometer screw gauge used for measuring length. You put whatever whose length you want to find, like the length of human hair. Sorry, I don't have some. If you put a nail or a wire across here like that, you can screw that in and it will record the diameter of the wire. Okay, so this one is saying that the reading here in inches, it's actually placed there in inches, or this one can be changed from centimeters to inches or millimeters. Okay, so the reading there is 0.25000. How many significant figures are those? Okay, the quality of an instrument is determined by how many significant figures it can give, or how many decimal numbers fall behind, how many digits fall behind the decimal number. That tells you how good an instrument is. And this particular instrument is very good because of those 5 decimal places behind the decimal number. So my question is, how many significant figures is that number? All right. Okay, now we want to go into manipulation with how to manipulate with significant figures. How do we add numbers, and what number of significant figures do we give the result when we add 2 numbers? So if you have 2 different numbers, each with its own significant figure, could be the same or could be different. Once you've added them, the answer will have a certain number of decimal places. When we report this answer, we must give it to a certain number of significant figures for good reason. So let's first of all see how we decide the number of significant figures we give to the result of addition or subtraction. If you're adding 2 numbers or subtracting 2 numbers, they could be decimal, they may not be decimal numbers. Round off the result to the last common decimal digit. We will explain that. Sometimes when you read this, it does not make much sense until you look at examples. So for example, express the sum or difference to the correct number of significant figures. And this is the rule we are going to use. So once you've added them, your answer should have the same number of decimal places as that of the least component, like this. Okay, so we are going to add 21.53, which is 2 decimal places, which has been given to 2 decimal places. And we're going to add 5.309, which, as you can see, is to 3 decimal places. Now when we add this, our answer must be to 2 decimal places. We must take the same number of the least number of decimal places. So our answer will have the same number of decimal places as 1 here, which is the smallest number of decimal places, which is to say we have 3 decimal places here and we have 2 decimal places there, so our answer will need to be to 2 decimal places. This is what this sentence implies. Okay, but I'll explain it in the processing here. So I'm going to add these 2 numbers. I will move this to the top of that like this. Okay, so arrange them so that the decimal points line up nicely. We know how to add numbers anyway. So if we add that, 0 plus 9 is going to give me 9, 3 plus 0 will give me 3, 5 plus 3 is going to give me 8, and then there's a decimal point there. Then 1 plus 5 will give me 6, and lastly I will have 2 down there. So you can see my answer, the result of the sum is to 3 decimal places. The rule is, and this rule applies to physics as well as for mathematics, that our answer, the answer that we give, must have the same number of decimal places of the last common decimal place. So if you look at this 21.53 and it ends there, but this one is 0.309, so the last, so 5 and 3 are common decimal place, 3 and 0 are also common, and the next one, 9, does not have a common decimal with the 21.53. So the last available common decimal place is 3 and 0, which means the second decimal place. So our answer must be to 2 decimal places, okay? Okay, so you look at that, that's the last common decimal place, so that tells us that our answer must be rounded off to 2 decimal places. Now pause the video and try to give an answer to what you think that value is going to be. Okay, since we are rounding off, 9 will round off the 3, so the 3 goes to 4, and our answer is going to be 26.84 to 2 decimal places, which also happens to be 4 significant figures. Okay, so if you're counting decimal places, decimal place refers to the digits that come after the decimal number. So there are 2 decimal places. But when you're looking for significant figures, remember this is a decimal number. So we start from the left and count all digits starting with the first non-zero digit. So we have 4 significant digits. Okay, this would be 5 significant digits. This would be 4 significant digits. This would be 4, like that. But it is 2 decimal places. This is 3 decimal places. Okay, like that. Let's see another one. All right, we are still adding and subtracting numbers. Express the sum or the difference to the correct number of significant figures. All right, so we have 0.03, which is to 2 decimal places. We will add 0.309, which is to 3 decimal places, and then we will subtract 0.0172, which clearly is to 4 decimal places. If we are going to add this, look at the 3 numbers. I could first of all line them up. If I line them up like this, you can see that the last common decimal point is the second decimal point there, like that. Okay, so that is the last common decimal point. Okay, so therefore our answer will have to be to 2 decimal places. Okay, so looking at that's 4 decimal places, that's 3 decimal places, that's 2 decimal places, so our answer must be to the smallest decimal place. Okay, so it's going to be to 2 decimal places. So now let's add these. So I'll move the 0.03 up and add them. Our answer will have to be to 2 decimal places. Please remember that. When we add that, we get a 9 there, a 3, and a 3. So 0.339 is our answer for adding the first 2. But now we have to take that and subtract this figure. So I'm going to move it up to this. Okay, so I will move that up there. Again, line the decimal places together, and now we are subtracting. So we borrow 1 from 9 and put here, so we have 10 minus 2. I hope we know how to subtract. So that gives me 8 Okay, first is 8. I was left with 8 there after I moved 1 there, so I'm left with 8 here. So 8 minus 7 is 1. Here I have 3 minus 1 should be 2, and 3 minus 0 is 3, and so we have 0.3218 as our result. Our final answer is 0.3218, but our answer has to be given to the correct number of significant figures. So if we're going to get correct number of significant figures, or the correct number of decimal places, we reason that our answer must be to the same number of to 2 decimal places like we reasoned before. And so we are going to have to round this to 2 decimal places, which becomes, if we round to 2 decimal places, that's just 0.32 as our final answer. So 0.32 is going to be our final answer, which is 2 decimal places and also the same as 2 significant figures. Since it's a decimal number, okay, we start counting from the left and we count all digits starting with the first non-zero digit. So we have 3 and 2, so there are 2 digits there, so 2 significant figures. Okay, I hope you are understanding this. I want you to try some of these out. All right, so if you go to the eWorkbook that we use in class, I have so the eWorkbook is problems. I want you to go to the problem set page from page 5 to page 7. The level is C, questions in level C, and you're answering questions from number 1 to number 8. Okay, just so that you remember, the link to the eWorkbook is included in the comment section. So if you go to the comment section, you'll find I have included a link to the eWorkbook. Okay, I've also included a link to a Facebook page where you can ask me questions if you have any. All right. Also, the next lesson we will do, this one continues, but the next lesson, which is U005 on significant figures, part 2, I will include solutions to selected number of questions from the eWorkbook. Okay, so all this I will solve some questions. So if you go to the next video, you should find a solution to a selected number of questions from level C. Okay, that brings us to the end of this section on addition and subtraction of digits. We go to multiplication and division. Now, before we go to multiplication and division of numbers and how to determine the resulting number of significant figures, I want to talk briefly about the scientific notation. There is a complete topic on scientific notation, so I'm going to spend just a short amount of time to talk about it briefly. If you already know about scientific notation, there is no problem. You can skip and go directly to multiplication and division of numbers and their significant figures. Okay, so briefly about scientific notation. The scientific notation is the method we use to write numbers. Sometimes numbers can be very, very big that we don't want to write all the digits. For example, the diameter of an atom is about 0.000000000. Those are 9. 0, I can put 1 here, 0.1 meters. This is the same as 10 angstrom. So this is the approximate diameter of an atom. If I was going to use this figure in calculation, you can imagine having to write it every time you want to start calculating, having to write this. That becomes very difficult. Similarly, so this is the diameter, the typical diameter of an atom. Okay, similarly, the mass of the Earth, for example, is about 5.98. In fact, let me write the whole thing as it is. So the mass of the Earth is about 598,000,000,000,000. That's 12 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 kilograms. So that is the mass of the Earth. And there are calculations that we carry out in physics that involves working with the mass of the Earth or the mass of the Sun and so on. You can imagine having to write figures like this every time you want to conduct a calculation. First of all, it is tedious writing this figure, but secondly, writing it every time and then trying to multiply with something the way it is can be very, very challenging. So in order to avoid having to write this, scientists or as mathematicians, we find a simpler way, a simpler notation that we can use to represent this number. For example, I would represent this number, this one here, as simply 1 times 10 power 10 meters. Okay? And I would represent this as 5.98 times 10 power 24 kilogram. So when I write it like this, it makes life much, much easier. Writing it like this is what we mean by the scientific notation. But how am I deciding these numbers? Okay, let's look at that. So consider the following numbers. Let's consider the following numbers. We'll start with 200. Now 200 can be expressed as 2 times 100, which in turn can be expressed as 2 times 10 to the power of 2. 100 is the same as 2 times 10 power 2. Okay? Let's look at another one. 135 can be expressed as 1.35 times 100. If we multiply 1.35 by 100, the two zeros mean the decimal point. The two zeros will make the decimal point move forward 2 steps, and we get 135. So by multiplying 100 by 1.35, we can get back 135. So I can write 135 as 1.35 times 10 to the power of 2, like that. Okay? Let's see another one. 52,000 can be expressed as 5.2, but if I put a decimal point there, then I need to multiply by 10,000 to get back this figure. So 5.2 times 10,000 will give me back that. So I can write 52,000 as 5.2 times 10 to the power of 4. So 5.2 times 10 to the power of 4. Okay, let's look at another one. What about 0.00726? Well, I can express this as 7.26 over 1,000, because when I divide 7.26 by 1,000, it causes the decimal point to move backwards 3 steps, which will bring it from between 7 and 2 to that point there. Okay? So 0.00726 is equivalent, or is the same thing as 7.26 divided by 1,000. Okay, so I can express this as 7.26 times 10 to the power of -3, because to get this I have to divide, because this over 1,000 means over 10 power 3, and by laws of indices, if we move laws of exponents or laws of indices, 10 power 3 can be brought up and it becomes 10 power -3. Okay, so notice that numbers that are less than 1, okay, decimal numbers, tend to have 10 to the power of negative here. Numbers that are bigger than 10 will tend to have 10 power positive integers here. So these are negative integers, these are positive integers. Numbers that are decimal numbers smaller than 1 will tend to have negative powers there of 10. Okay? Let's see another one. 0.21 is another number that is less than 1. So we can write it as 2.1 divide by 10, because if I divide by 10, the decimal point moves back 1 step, which will be equal to that. So I can write this as 2.1. This 10 is the same as 10 power 1, but if I bring it up, it becomes 10 power -1. So I can write this as 2.1 multiplied by 10 to the power of -1. Okay? Lastly, there is 7. I can express 7 as 7 times 1, or 7 divided by 1. But 1 is also the same as 10 to the power of 0. Any number to the power of 0 is 1, so I can use 10 the same way I'm using 10 here. So I can express 1 7 times 10 power 0. Okay? All right. When you express numbers like this, when we express numbers like that, when a number is expressed as another number here, times 10 power something like this, such that this number, the number that comes first, is lying between 1 and 10. Notice that all the numbers that I've chosen are similar in terms of the digits it contained. Okay, they are similar, except these numbers all fall between 1 and 10. So when you express a number such as this, like this, so that the first number is lying between 1 and 10, same digit as that, these are same digits as this, but what I have here must lie between 1 and 10, and then I say times 10 power some integer. This is what we refer to as the scientific notation. So the numbers on the left-hand side have been expressed in scientific notation. In other syllabuses, we also say in standard form. So this is called the standard form or the scientific notation. Okay? So I'm going to generalize down there. So any number n can be expressed as a times 10 to the power of k, where a is a number with the same digits as n, but my a must lie between 1 and 10. And k is an integer. Whether k is positive or negative depends on that number. If that number is less than 1, then k will always be negative. If that number is greater than 10, if the number is greater than 10, then k will always be positive. But if the number lies between 1 and 10, such as 7 lies between 1 and 10, then k will always be 0. Okay, so that's what I want you to remember about writing numbers in scientific notation. Let's see if we are getting this. Let me summarize. We are saying any number n can be expressed in the form a times 10 power k, where a is a number with the same digits as n and in the same order, but a lies between 1 and 10. A can take a value of 1, in other words, inclusive. A lies between 1 and 10. A can be equal to 1, but a cannot be equal to 10. Okay? And k is an integer whose value is the number of decimal positions moved in forming a from n. So if I'm going to form, let's use an example here. Express the following in scientific notation. So let's start with this. 345, we want to express this in scientific notation. So I'm going to say, we are going to write our value of a there, and then we'll say times 10 to the power of k. So we'll write the value of k up there. So what value do we put here and what value do we put there? Please pause the video and try it out yourself, and then check back what we are getting. Okay? So 345, the number with the same digits in the same order that lies between 1 and 10 has to be 3.45. Has the same digits in the same order, but lying between 1 and 10. So 3 lies between 1 and 10. You cannot put 34, because 34 is greater than 10. You cannot put 0.345 because that would be less than 1. So it has to be 3.45, okay? Now, the value of k is what you get by looking at our n and our a. The decimal point for 345 would be just after 5. How many decimal places has it moved to go to be between 3 and 4 here? Well, we can see that it moves 2 decimal places. It has moved 2 decimal places, and 345 is a number greater than 10, so the value of k has to be positive, and it is 2 because it tells us the number of steps that we have moved. Okay, and so 345 in scientific notation is expressed as 3.45 times 10 to the power of 2. That's simple. Let's look at another one. Okay, 0.18. So 0.18, what is the value of a there, and what's the value of k? Well, this number is less than 1, so we expect k to be negative. The number we put here should have the same digits as this, but must lie between 1 and 10. So the number with the same digits lying between 1 and 10 would have to be 1. You can pause the video. Should be 1.8. Okay? And now, how many decimal places do I move from, this is n, when I take n and make a, how many decimal places have I moved from here? We've moved one step to move it between 1 and 8. And so our answer here is 1, and it is negative because that number is less than 1. Like that. Let's see one more. Okay. 28,000 in scientific notation. What do you think you would get for that? Okay, so in this case 28,000, the number with the same digits would have to be 2.8. We can ignore the 3 zeros there. So 2.8, and how many decimal places? So this has to be positive because that number is greater than 10. How many decimal places have we moved? Well, on 28,000 the decimal place just comes after the last zero there. So how many decimal places do we move so as to place it between 2 and 8? That would be 1, 2, 3, 4. And so we can say this is times 10 to the power of 4. Just like that. Okay? Right. Next one there. This is just to help you understand what scientific notation is, if we wanted to write number in scientific notation. Here's another one. This one is less than 1, so we expect k to be negative. Okay? Well, a number here with the same number of same digits in the same order, 4, 5, 1, has to be, that's what we're going to put there, multiply by 10 to the power of k. So k takes that spot. So this number has to be, pause the video and try. Okay, so that number has to be 4.51, the number lying between 1 and 10. And how many decimal places have I moved to move this decimal point from here so that it goes between 4 and 5? That would be 1, 2, 3, 4. There are 4 of them. And so this is 10 power 4. But negative. Why? Because our number is less than 1. All right. Do I have any other? Yes, I think we have one more. 13.6. Express that in scientific notation. That is going to be, all right. So 13.6. This number is greater than 10. So it's not in scientific notation. So this has to be, this is going to be 1.36 times 10 to the power of, okay, 13.6 is greater than 10. So we expect k to be positive. But how many decimal places do I need to move that so that it goes between 1 and 3? We only move 1. And so this is going to be to the power of 1. Okay, so 1.36 times 10 to the power of 1, and we have expressed the numbers to the left in scientific notation. I expect you to know how to do this henceforth. Otherwise, you can look at this again in the next sub-unit that we'll be looking at. But otherwise, now we move on to the next question. The reason I had to do this is because some of the questions in the workbook are going to be talking about scientific notation, and you need to know the scientific notation to be able to solve those questions. Okay, so now here are those instruments again. This time, the readings, what you want to do is write each of the reading in scientific notation. So here's the first one, the same instrument we looked at earlier. Okay, express each reading in scientific notation. So 480, the reading on the voltmeter, express that in scientific notation. Okay, express the reading on the infrared thermometer, express that reading in scientific notation, please. Next is the reading on that analog thermometer. It is 68 or 67-ish. Okay, express that in scientific notation. Next is the pH meter, reading 7.474. Express that reading in scientific notation. Then we have, of course, the digital micrometer, which measures length in inch. This one measures in inches. Express that reading 0.25000. Express that reading in scientific notation. All right, and now we can move on to the next part. Okay, let's move on now. Now we want to see how multiplication affects the number of significant figures of the result. Okay, so we have two numbers that we want to multiply together. One has a different number of significant figures, maybe decimal places, compared to the other. Once we've multiplied them together and come up with an answer, what number of significant figures should the answer have? All right, so we want to see that. All right, so the rounded result has the same number of significant figures equal to the least available among the component. Okay, but now we are talking significant figures. That time it was decimal places that was the least. So our answer had, when we are adding or subtracting, our answer has the same number of decimal places as that was the least decimal places. Here, our answer, when we multiply or divide two numbers, our answer will have the same number of significant figures now as the number of significant figures that is available among the components. Okay? So in addition and subtraction, we are thinking decimal places. In multiplication and division, we are thinking significant figures. So let's look at an example. All right? Express the product or quotient to the correct number of significant figures. The product, so the result of multiplying, the quotient is the result of dividing. Okay, here is the first one, 21.53, which is to 4 significant figures, because now we think significant figures, and we want to multiply that by 5.30, which, remember, it has a decimal point, so the number we count from the left, starting with the first non-zero digit and counting everything. So there are 3 significant figures there. So when we multiply, I'm not actually going to go into the multiplication steps. I'm just going to put an answer. You can use your calculator to find this result quickly. So I'm going to put this up there. All right, and then I am going to multiply. All right, I am not doing the steps, I'm putting the answer there directly, and we find that the answer of that product is 114.1090. Okay, do we leave that answer like that to 4 significant figures, to 4 decimal places? How many significant figures is this? If we were to leave it like this, this would be 1, 2, 3. We are counting from, it's a decimal number, so we count from the left. So 3 and 4 is 7. So this is 7 significant figures. But the rule is that our answer must be rounded off to have the same number of significant figures as the component that has the least number of significant figures, which is to say that our answer needs to be to 3 significant figures because it is the least of the 2. Okay? So we round this so that it is to 3 significant figures. If we do that, we can see that all this we need to get rid of. The 0, the 9, the 0, and the 1 need to go so that we are left only with 114 if our answer is to be to 3 significant figures. So we are going to select the lowest number of significant figures, and that is what our answer is also going to be. Okay, so our answer is 114 to 3 significant figures. Okay, our answer must have the same number of significant figures as that is smallest among the components we are multiplying. Okay, I hope you understood that. Let's see another one. Okay, 20, which is to 1 significant figure. All right, because it's a whole number, so we start from the right. Whole is right. Start from the right and count all digits, but starting with the first non-zero digit. So we start with the 2. So that gives me 1 significant figure, and I'm going to divide that by 0.0410. Okay, this is a decimal number, so we start from the left and we can see that that should be 3 significant figures. Okay, if we are going to divide these two numbers, once again I'm going to put this above it, and then I will divide. Use your calculator to divide this, and if we do that, if we divide these two numbers, 20 divided by 0.0410, we get a value of 487.80488, and it continues. It's actually 87 and so 9 and so on. Okay, so just the value that I've put there is already, I think that is 8 significant figures, but our answer needs to be to the same number of significant figures as the least there. So if you look at that, what must our answer be? I'm not sure I put this there, did I? Yes, so we have to write this as 500 so that it is to one significant figure, because it has to be to the same number, the smallest number of significant figures among the components that we are multiplying or dividing. So our answer has to be to one significant figure. So round this result up so that it is to the correct number of significant figures. So that gives me 500 to one significant figure. Okay, I'm hoping you've understood that. Problems that include powers of 10, and so here is where the idea of scientific notation comes in. All right, simplify, write answers in scientific notation. So simplify this problem and write your answer in scientific notation to the correct number of significant digits or significant figures. Okay, so here is a product, so 6.317 times 10 power 3. So the number has been given in scientific notation. The dot means multiplication, of course. And we are multiplying this by 0.8902 times 10 power 3. Please pause the video and explain why this is not in scientific notation. This one is in scientific notation, but this one is not in scientific notation. Why is that? Okay, try that out. All right, but now let's continue. So I'm going to write these figures without the brackets in them. So we have 6.317 times 10 power 3 times 0.8902 times 10 power 3. What we want to do is to collect. These are multiplication, so I can move them around. So I will move 0.8902 to the left so that it multiplies that, and 10 power 3 with 10 power 3 so that I can add them, I can multiply them using my laws of indices or exponents. So if I move them like that, so now I'm going to multiply these two. If I multiply those two there, I get a value of 5.62. Use your calculator, please. 5.62339 is my result. And when I multiply equal bases, so the base is base 10 and base 10 by laws of exponent, the exponents are going to add up. So that group of numbers is going to give me 10 to the power of 3 plus 3, which is 10 to the power of 6. Now, is this the answer? Not really, because we are multiplying. Our answer has to be to the same number of significant figures as that of the one that is least. Now this number here, so you ignore the 10 power 3, the 10 power 3 there, just look at these numbers, the two numbers here. We can see that that is to 4 significant figures, and this is also 4 significant figures. So our answer needs to be to 4 significant figures. Okay, so round that number there so that it is to 4 significant figures, and as you can see, it's going to be 5.623 times 10 to the power of 6, answer being given to 4 significant figures. So when we talk about the significant figures, we are actually looking at the number, ignore the 10 power k. Okay, so that is the number 5.623 times 10 to the power of 6 is the answer written correctly in scientific notation and to 4 significant figures. Okay, you can always rewind the video so that you are sure you've understood what we did. But let's look at another example. Okay, here's another example. 1.12 times 10 power 9, which is already scientific notation. We want to divide that by 7 times 10 power negative 4, which is also correctly in scientific notation. we want the answer to this, and when we get our answer, we must express it in scientific notation and also with the correct number of significant figures, okay? So we can see this is 3 significant figures and this is 1 significant figure, okay? So we are going to divide 1.12 by 7. We're going to deal with that by itself, and that gives me 0.16, okay? Similarly, we're going to multiply by 10 power 9 divide by 10 power negative 4, and using the laws of exponents, that should give me 10 power 9 minus negative 4, laws of exponents. When we divide, we subtract, okay? So that is 10 power 13 there, so we have 1.6 times 10 power 13. Now, 1.6 in scientific notation is, I'll write it here, 0.16 in scientific notation is going to be 1.6 times 10 to the power of, how many decimal digits have I moved from here so that I take it between 1 and 6? It is 1 decimal place, but the number is less than 1, so this has to be negative. So I can express this thing here, so I can write 0.16, I can write it as 1.6 times 10 power negative 1, that's just this bit. And then now I multiply by the 10 power 13, if I multiply by 10 power 13, then I can use the laws of exponents here, and I have 1.6 times 10 to the power of, you add the exponents and we get 12. And so this is going to be my answer. However, the lowest, okay, so this is supposed to be the answer, except this number here is to 3 significant figures, and this one here is to 1 significant figures. So my answer must be to 1 significant figure. This is 2 significant figures, so I can't leave my answer like that. So I have to round it off so that it is to 1 significant figure. Okay, so let's see. So this is how I get this result. I hope you understand. You can pause and look at it again slowly so that you understand what we have done. Okay, okay. And so we can express that as 1.6 times 10 to the power of 12 based on what I just did there. And because my answer has to be, this is 3 significant figures and this is 1 significant figure, so my answer has to be 3 significant figures. This is 2 significant figures, so I can't use that as my answer. So if I'm to round it so that it is to 1 significant figure, 1.6 is closer to 2 than it is to 1, so my answer is going to be 2 times 10 power 12, and this is now to 1 significant figure. I'm hoping this is clear. There are questions in the eWorkbook. I would like you to try those out. Okay, so eWorkbook problem set can be found on page 8 and 9, and this is under level D, question number 1 to question number 4. Once again, the link to the eWorkbook can be found in the comment section, and when I complete the video on significant figures part 2, that video will include solutions to a selected number of questions from the ebook. Okay, right, so go and try those questions out, and then check out video number 2 on this on significant figures to see how those questions, some of those questions are solved. All right, hoping that you are able to understand the lesson. If you found some of the concepts difficult, please don't forget to send a message. Put your messages in the comment section, or send me, or go and type it in the Facebook page. And otherwise, if you're seeing this for the first time, please don't forget to subscribe to the channel and click the notification bell so that anytime a new video appears, you will be notified promptly. Also, please consider sharing the video with other students who might find the material that we are covering useful. This material on significant figures especially is not just useful for mathematics, it's going to be important even key in the study of physics. In the IB diploma, writing your answers to the required number of significant figures is very, very important in physics. Okay? I believe that brings us to the end of this section. I will see you in the next video.